Okay, so last time we introduced this notion of equitable partition of a graph. So I think the definition we have here is it's a partition into m non-empty subsets of vertices. We call them x1, x2, xm. The property that you have these numbers, bij, so you have m square numbers, so bij, I and j between 1 and m, such that if you take any I and you take any j, and you pick any vertex x in xi, and you look at the number of neighbors that x has, the neighbors that live in xj, this number does not depend on x, it depends on just on I and j, and it equals this number bij. So bij is called the quotient matrix of the equitable partition. We did some examples here, I won't go through them. And then we essentially proved this result that if you have an equitable partition and P is the characteristic matrix of the partition, so P is a matrix, is a tall matrix, whose columns are the characteristic vectors of the subsets of the partition. So it has m columns and n rows. Then A times P equals P times B. And I mentioned last time that these two things we'll see in this class, they're actually equivalent. Being an equitable partition is equivalent to AP equals PB. But for now, we just prove this implication that if you have an equitable partition, then AP equals PB. And to do that, we just did matrix multiplication, and each of the matrices AP and PB are tall matrices. So their rows are labeled by the vertices in V, and their columns are labeled by the subsets of the partition x1, x2, xm. And we show that for the entries of these matrices are the same. So this is the key equation. So we have AP equals PB. Now today we'll pick it up here, and so we have the second part about B equals this seemingly complicated formula. So let's see how we get there. So what do we have? We have AP, let me write it in red, have AP equals PB. And what we like to get from here, we like to get rid of the P on the left-hand side and find some kind of formula for just B itself. But now, remember that P, you cannot just, it doesn't have an inverse necessarily, because P is a tall matrix, so it's of this form. But now, what kind of properties do we know for P? Well, we know that from definition, the columns are the characteristic vectors of this x1, x2, xm. And now, if we take P transpose, so we flip the matrix P this way. So this is let me write it here. This is P transpose, and so you have these rows corresponding to x1, xm, and you multiply it with P. What are we going to get? Well, we get a matrix that is m by m. So you have it's indexed by x1, x2, xm. And now this will actually be a diagonal matrix because these subsets of vertices x1, x2, xm are disjoint. So when you take the dot product between the characteristic vectors of, let's say, xi and xj, if I and j are not equal, that dot product will be 0. And if I and j are equal, that dot product will count a 1 as many times as the number of elements in xi. So this will give you, on the diagonal, we have cardinality of x1, blah, 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 cardinality of xm, and 0 everywhere else. So essentially what I wrote here is that P transpose times P will equal the diagonal matrix, whose diagonal entries are the cardinality of x1, cardinality of xm. And this is an invertible matrix because it has, it's a diagonal matrix and all the entries on the diagonal are non-zero, okay? So this is the idea to get rid of the P on the left-hand side there. So from here, what we do is we multiply to the left, multiply by P transpose. So we get P transpose AP equals P transpose P times B. And now this P transpose P becomes our friend here, and we can get rid of it by multiplying by its inverse, because this matrix is invertible. And so we multiply again here, multiply to the left by P transpose P inverse, and we end up with P transpose P inverse P transpose AP equals B, which is exactly the second part of our equation. That basically B, I'll just write it this way. Okay, this is what we proved. Now, okay, where are we going with this? Well, before we state the main result of this part, let me just say one quick thing. One observation is that B is not symmetric in general. We've seen examples, so this is clear. We've seen examples where B is not symmetric. However, B is similar to a symmetric matrix. So if two matrices are similar, they have the same eigenvalues, and a symmetric matrix always has real eigenvalues. So that will imply that B has real eigenvalues. Okay, and we'll have M real eigenvalues, including multiplicity. Now, how do you show that B is, so how do you show this, this part here, that B is similar to a symmetric matrix? Well, it follows from the previous result. So B was this P transpose P minus 1, P transpose AP. And now, I hope I won't confuse you if I call this P transpose, let me call it K, and let me call this thing M. Now, P transpose AP, this should be clear, this matrix is symmetric. Okay. And so what we have is that this equals K inverse times M. And what we can do is K is this diagonal matrix. So K is a diagonal matrix with cardinality of x1, blah, 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 cardinality of xm. I define K to the power minus 1/2 to be the matrix whose diagonal entries are cardinality of x1 to the power minus 1/2, cardinality of xm to the power minus 1/2. Okay. And now from the equation, so what do we have? We have B equals K minus 1m. I can multiply to the, what do? I multiply to the left by K 1/2. So I define K minus 1/2. You can define K 1/2 similarly. I guess I didn't do it. Let me squeeze it somewhere here. K 1/2 is diagonal x1 to 1/2, xm to 1/2. So you multiply to the left by K to 1/2. So you get K 1/2 B equals, when these two matrices K to 1/2 and K minus 1/2 meet, you get K to the minus 1 meet, you get K minus 1 M. And now at the next step, you multiply to the right by K to the minus 1/2. And what do we get is K 1/2 B K minus 1/2 equals K minus 1/2 M times K minus 1/2. So now I leave it to you. I mean, so this matrix here on the left-hand side is something that is similar to B, because you have an invertible matrix on the front and its inverse on the right. And I leave it to you to show that the matrix here, so you have M is symmetric, and now you're multiplying it by this diagonal matrix, and this diagonal matrix, it equals its it equals its transpose. So every diagonal matrix has this property. So this, the matrix here on the right is actually a symmetric matrix. So that essentially this equation proves that B is similar to a symmetric matrix. Okay. All right. Now, for us in graph theory, why do we care about this? So this is a theorem. So as before, we have a graph, and let me write it here. Let gamma graph, and assume that pi is an equitable partition of gamma with a quotient matrix B and characteristic matrix B. So then two things will happen. So we'll prove them here. One, the minimal polynomial of B divides the minimal polynomial of A. And actually something stronger will happen is that the characteristic polynomial of B divides the characteristic polynomial of A. So the way we'll use this, we'll use the second part, that's the stronger part, but the way we'll use this, this is used in spectrograph theory, is you find this equitable partition. B is usually a smaller matrix for which you can find its eigenvalues easier. And then by this theorem, the eigenvalues of B will be eigenvalues of the big matrix. Okay, so let's prove this. We'll do first part, which is a bit easier. So because we have an equitable partition, we know that AP equals PB. And now I'll leave it to you to show that if you use induction on K, you can prove that AK times P equals PB to the power K for any K natural number. Let's just do one step and then you can see the pattern. So for example, I have AP equals PB. So if I want to calculate A squared P, this is A times AP. What is this? Well, this is A. AP, I replace it by PB. So you replace AP one at a time by PB. And so I get this, but I can play this game again. This is AP times B, but this is PB times B, and this is PB squared. So that's how you can prove. Okay, and so you can prove this fact, and using this fact, you can also prove. So from here, it follows that actually FA times P equals P times FB for any polynomial F. Because if the relation, you have this relation of in the red rectangle satisfy for any powers of the matrices A and B, then a polynomial is just a linear combination of such powers. So this result is I don't think is that surprising, and it shouldn't be. It's not difficult to prove. And now to prove the assertion, what you do is we take F to be the minimum. I'll just call it like this: min A, the minimal polynomial of A. Okay, so as you remember, the minimal polynomial of A, by definition, is the monic polynomial of smallest degree, such that where the matrix A vanishes. So you can take, I mean, maybe not mean A there. Let me just change a bit this notation. Sorry about that. Let's just put mean A like this. So it's a f of x is mean A of x. Okay. So essentially A vanishes. It's the same thing as f of A equals 0. So in our situation, we have that mean this polynomial. If you plug in the matrix A in it, it gives you 0. 0 as in the 0 matrix. Okay. And so if you take f, if you plug in there this polynomial mean A, what you get is, so from this equation here, when you replace f by mean A, that becomes 0. And so we get on the left hand side, you get 0, and on the right hand side, you get P times mean A with the matrix B inside it. And by the properties of minimum polynomials, it's easily to show that this implies that the minimum polynomial of B must divide minimum polynomial of A. Okay. So now this is not so bad, but again, the second part is stronger, and we have so for the second part we want to talk about characteristic polynomials. So we want to prove that the characteristic polynomial of B divides characteristic polynomial of A. Okay. So now the first step is that we know that the columns of P are linearly independent. And then in R, let's say n is the number of vertices, okay? And that's easy because they're orthogonal to each other. They're like, they're these characteristic vectors of, so P, remember again, P is this tall matrix, and its columns are the characteristic vectors. So its columns are the characteristic vectors of x1, x2, xn. Okay. So now they form a linearly independent subset of vertices, subset of vectors in Rn, and you can always extend. This is one of the first things you learn in linear algebra, that you can always extend it to a basis. So therefore, there exists a matrix Q such that the columns of the matrix P, and then you put Q next to it. Maybe I don't need the bar. PQ form a basis for Rn. So P, this is so if you look at the matrix PQ, from here to here you have m columns, and so you need to add n minus 1 columns, and here you have n rows. So essentially, because the columns of this matrix form a basis for Rn, this matrix is invertible. Okay. And now, so what does it, well, so these columns form a basis. So any vector in Rn can be written as a linear combination of the columns of this matrix PQ. So therefore, what we can apply this to the vectors, the column vectors of the matrix A times Q. So when we do A times Q, again, A is a big matrix, n by n, and Q is a tall matrix. So what we get is this is a tall matrix. It's n by n minus m. But the columns, the vectors here are written as a linear combination, are in the column space of this matrix PQ, and therefore they can be written AQ. Okay, each of these column in this matrix can be written as a linear combination of vectors of the columns of P and Q, and therefore AQ equals something of the form PC plus Q times D. Remember from linear algebra, anything that's in the column space of a matrix can be obtained by multiplying that matrix to the right by a certain vector. Okay, so that's why this you can write this in the following. So my point here is that there exist C and D matrices such that AQ equals P times C plus 2Q times D, with C and D of the appropriate dimensions. I mean, you can work them out. So here A is n by n. I'll put it here. Q is what? It's n times n minus m. P is what? P is n and m. So Q should be m and n minus m. And Q is n and n minus m. So Q is, I think, maybe square n minus m. Something like that. Okay. So then, how does this help us? Well, we have two things. From the previous part, we have AP equals PB. And now we did AQ, and we wrote AQ as a linear combination of PC plus QD. And you see there is a 0, there is no D in this part. It's just PB. And there's no Q in this part, okay? So now, from here, we will write this in a different way. And the way we write it is as a matrix equation in which we multiply A by the matrix P, Q, okay, to the right. And this is like a block multiplication. So you have A multiplied by this matrix that has two blocks, P and Q. And so this will equal AP and AQ. And what is AP? Well, AP is P times B. And what is AQ? I'll give some space here, is PC plus QD. And here comes the trick. So it helps to be familiar with these matrix multiplications. This part is the same thing as multiplying PQ from the left, in the left, by the matrix P, B, C, 0, D. So if you start from the back here, if you start from what I wrote at the end, PQ. So when you multiply the matrix PQ by this 2x2 block matrix, in the first step you get PQ meets this part B0, and so you get PB plus Q0, so you get PB, so that's correct. And in the second step you get PQ multiplied by this part CD, and you get exactly what's on the outside. Okay. So now what does it mean? Well, if you look at the beginning, we started A times PQ, and what did we end up with? We ended up with PQ times something, but PQ is invertible, so we can get rid of PQ here. So we multiply PQ to inverse A times PQ equals B C 0 T. So what does that mean? Well, this matrix here, this is a matrix that is similar to A. So therefore it has the same characteristic polynomial. So remember, let me just write by phi. And if we are not sure which matrix we're talking about, I'll put it as an index. Phi of x is determinant of xi and minus a, the characteristic polynomial of A. So from this relation, we get that phi A of x equals the characteristic polynomial of this matrix on the left-hand side, because similar matrices have the same characteristic polynomial, and that will equal the characteristic polynomial of the matrix. I won't write this as an index, the characteristic polynomial of that matrix, but what is the characteristic polynomial of that matrix? That will be 5bx times 5dx, because it's upper and a block upper triangle. So from here you get that 5bx divides 5ax. Okay, and that's the second part. Okay. All right.
I have a question with
with
the characteristic of the BC0D matrix. So is that just a trait of all block matrices that you can just consider the characteristic parts of like B and D in this case?
Well, in this case, you have this 0. If the 0 wasn't there, then
okay.
Yeah. So in this situation, I mean, it's essentially like if you were to do a determinant expansion, like if I were to do
okay.
If you know, like it's partitioned like this, and when you do a determinant expansion, the only non-zero things will be when you take something from here and something from here, because if you're picking something from here, from the C part, then you're going to have to pick something from this side, and that will kill that term. That does it make sense?
I get the big picture. Yeah.
So that's that. You can essentially just go from the definition. Well, the definition, depends on how you define your determinant and your, but if you do this expansion after all the entries and all the permutations in SN, you pick one entry from each row and each column. You are forced to pick things from here and here, because in that expansion, whenever you pick some things from here, it forces you to pick some things from the bottom, and that part kills you. It's a 0, so you get no contribution. So that kind of explains this result here. Okay. All right. Let me see what I wanted to show. Okay. So this is one theorem. Okay, so we'll see some example in a second. Let me give you the second part. There's another part to it. Well, I'll write it as a proposition. So we have the same scenario with a graph, and we have phi is an equitable partition. Of phi with quotient matrix P. So from the previous part, here's where I'm trying to get. From the previous part, this second result, we have that the characteristic polynomial of B divides the characteristic polynomial of A. So the matrix B is M by M. So from here, we will know M eigenvalues of A. From here, we will know these eigenvalues because they're eigenvalues of B. So the question is, what can we say about the other? Because the spectrum of A contains n eigenvalues. So how can we look for the other? Where are the other eigenvalues of the matrix A? Can we use this equitable partition to get to that? And it turns out we do. So to do that, let's prove two things. So one is that if V is an eigenvector of B, then PV is an eigenvector of A with the same eigenvalue. Okay, So in this situation, what one sometimes can be said is that the eigenvector v of b, you can say lifts. I'll explain this in a second. To the eigenvector PV of A with the same eigenvalue. Okay. Now the second part is that the eigenvectors of A can be split into two parts. Well, I mean, it's more precise, it would be like we can find a basis of eigenvectors of A such that we can split them into two parts. So let's say part A, the eigenvectors that are constant on the sets x1, x2, xm. So they have the same, if you pick one of these subsets xi, on each vertex of that xi, these eigenvectors have the same entry. B is that the eigenvectors that are orthogonal to the characteristic vectors of x1, x2, xm, essentially they sum up to 0 on each of these sets. Okay. So let's let me do quickly first part, and then we can take a short break. So proof. So for the first part, we have that V is an eigenvector of B. So let's say with some eigenvalue theta. So V is not 0, and B times V is theta times V. So again, this V is in Rm. So it's a smaller vector, okay? And now from here, we want to say something about PV. So what we do is we do this calculation, A times PV. Now, I'll tell you in a second what this PV will look like. So what this equals AP times V, and we use again the equation that AP equals PB. This is the key everywhere. You get, it replaces it by PB times V, P times BV, and that's P times theta V, and then that's theta times PV. Okay. Now, what is PV? Well, so V, the entries in V are indexed by x1, x2, xm. In PV, give it a different color. The vector PV here, the way you can think of it is PV. Let's say that the smaller vector V has some entry V1, blah, 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 Vm. So V1 is on X. Now, let's say that in my big, so the bigger vector PV is has dimension n. Its entries are indexed by the vertices. And so let's say X1 is in the first positions. Well, PV, the entry of the vector there is going to be V1, V1, V1. So in some sense, this is kind of what I mean by lifting. You have this small matrix B, which is m by m, and you have this vector of dimension m, and it has these entries V1, V2, Vm. Now, because the partition is equitable, what is going to happen? This vector, it will give us, for the big adjacency matrix A, it will give us this eigenvector PV with the same eigenvalue, but essentially the V1, which corresponds to X1 in V, will become V1 for every vertex in X1. And similarly, if you have X2 here, you get V2, V2, V2 everywhere, and so on. Okay, so that's this first part. Okay, so I'll stop here.